Okay, students, so welcome back. Right, so now we are going to continue from MCQ number 11 to MCQ number 20 of AS Physics 9702. And this is May June 2010 variant 2. All right, it's paper 1 2. It's paper 1 variant 2. Let's get started. Okay, MCQ number 11 says the two equal masses they travel towards each other on a frictionless air track at a speed of 60 centimeters per second and 40 centimeters per second. What is the speed of the masses after the impact? Okay, over here we are going to apply the law of conservation of momentum. We know that momentum is a vector quantity, so since they are moving in the opposite directions, we are going to have to consider one of them to be in the negative direction. Right, the velocity of one of them should be negative. I assume the right hand side to be positive and the left hand side to be negative. So this means that the velocity of 40 centimeters per second is negative 40 centimeters per second because it's traveling in the opposite direction to the positive direction. Now, the total momentum before collision. Momentum is the product of mass and velocity, right? Our masses are the same, so I've assumed the masses to be m. Okay, the total momentum of the 60 centimeters per second, the left one is 60m plus the total momentum of the right hand side one is minus 40 multiplied by m. Minus 40 because it's in the opposite direction. Add them up, the total momentum before collision is 20m. Now, what about the total momentum after collision? Okay, after collision, they told us that they stick to each other, all right? They stick on impact. Okay, sticking would mean that the total mass after collision is 2m, all right? So the total momentum after collision is going to be 2m multiplied by v. We need to find v, all right? Now, law of conservation of momentum tells us that total momentum before and after collision are equal. So this would mean that this 2m into v is going to be equal to this 20m. So the answer that we get for v is equal to 10 centimeters per second. So our option A is correct. Now let's move on to the next MCQ. Okay, over here it's forces of 3, 4 and 5 Newton act at one point on an object. Now the angles at which the forces act can vary. Okay, what is the minimum resultant force of these forces? All right, so let's calculate this. Okay, I assume this point to be the point from where all these forces are being applied. Okay guys, if you notice one thing, this is a 3, 4 and 5 Newton. These are 3, 4 and 5 Newton forces. There is a special triangle in math, 3, 4, 5 triangle. It is a right angle triangle. And by the way, the 3 and 4 through Pythagoras theorem, this 3 and 4, this triangle has an hypotenuse of 5, okay, and a base of 3 and a height of 4 Newton, of 4 units basically. This is a special triangle in math. All right, so now in this case we can also form a special triangle. Let's assume that this is a special triangle. Okay, so if 3 Newton is one force acting towards the right hand side, okay, let's assume that the 4 Newton is the other force acting upwards from the same point. Okay, I've drawn the point over here. Okay, just forget about this point. This is a new point over here. 3 Newton to the right, 4 Newton upside, and 5 Newton, let's assume that it's traveling, it's being applied over here towards this side. Okay, just forget the 5 Newton force. Now, first of all, let's try making out the resultant of the 3 and 4 Newton if they both are acting at 90 degrees to each other, because the examiner told us that the angles can vary, so we can consider any of the angles. All right, so now if for 3 and 4 Newtons have an angle of 90 degrees, so the resultant is going to be 3 Newton plus 4 Newton will have a resultant of 5 Newton acting in the opposite direction. But now we still have a 5 Newton force separately as well. This 5 Newton is due to these two forces collectively acting at the point, but we can also have another 5 Newton force which they gave us. If this 5 Newton force acts on this point in the opposite direction to the resultant, then the two 5 Newton forces will cancel each other out and the minimum resultant that we'll get is 0. So A is the correct answer. Let's move on to the next MCQ. Okay, an object is immersed in a liquid in a tank, experiences an upthrust force. Okay, upthrust is a force due to densities, difference in densities in liquids. Okay, what is the physical reason for upthrust? Okay, the density of the body differs from that of the liquid. Well, no, upthrust is a force that is applied due to difference in densities within a liquid or within a medium. All right, the density of the liquid increases with depth. Yeah, this is a correct fact. Yes, it does increase with depth because actually, wait, its density stays constant if the liquid is the same. But let's see, The pressure in the liquid increases with depth. Yes, pressure increases with depth. And the value of G in the liquid increases with depth. No, the value of G is constant. It depends upon the planet at which the experiment is being performed. Value of G is the gravitational field strength, or it is the acceleration of free fall, right? And acceleration of free fall actually depends upon the planet at which the experiment is being performed. It depends upon the gravitational pull of that planet. Okay, B and C, there is a tie between B and C. Okay, now if we look at B and C, actually this upthrust is not due to the density of the liquid, but rather it's due to the difference in pressures. Okay, difference in pressure within the liquid. If I have a liquid over here at the depth, at a greater depth, the pressure exerted at this point will be greater than the pressure exerted at some other point which has a smaller depth as compared to the other depth. All right, because pressure in liquids can be calculated by using the formula rho gh, where rho represents the density of the liquid, g represents the gravitational field strength, and h represents the depth of the liquid. All right, so since we know that yes, the depth does change, and if the depth changes, the pressure also changes. So upthrust by definition is actually a force that is exerted from the more pressure from the deeper side to the less deeper side. From the deeper to the shallower side, the pressure is exerted. So it's due to the difference in pressures that upthrust force exists. So it's actually option C. The pressure of the liquid increases with depth. That's why upthrust exists, because the pressure changes in liquid with depth. Okay, so it's gonna be C. Let's move on to the next MCQ. 40 inclined plane. A brick weighing 20 Newton rests on an inclined plane. Okay, it's resting. It's in equilibrium. The weight of the brick has components 10 Newton parallel to the plane. Okay, this is actually the component of the weight. Okay, inclined plane. If we take a step back and review our theory part, the mass acts downwards, the weight acts downwards, mg. The component of weight parallel to the plane is mg sine of theta, right? And mg sine of theta is equals to 10 Newton, whereas theta represents this angle. Now the brick also experiences a frictional force of 4 Newton. What is the acceleration of the brick down the plane? Assume the acceleration of free fall to be 10 meters per second squared. All right, what is going to be the acceleration of the brick down the plane? The brick also experiences this. It is of 20 Newton. All right, 20 Newton is actually its force. Okay, 20 Newton is the weight of the brick. All right, it rests. The weight of the brick has a component of 10 Newton down the plane. Okay, 10 Newton is acting downwards over here. Okay, it's 10 Newton that is acting over here. Okay, it's labeled. Then the brick also experiences a frictional force. Okay, now what is the acceleration of the brick down the plane? All right, we need to calculate the acceleration. Okay, to calculate the acceleration, the formula is pretty simple. First of all, we know the weight of the brick, right? We can calculate the mass of the brick using the weight of the brick. We know that weight is 20 Newton. 20 is equal to mg. All right, and the mass of the weight is gonna be 20 upon g. G is 10 as given in the question. Mass of the brick is 2 kgs. Okay, we have the mass of the brick now. We need the acceleration. Okay, from Newton's second law, we know that the net force equals F. F is net force equals the product of mass and acceleration. We have the mass. What's the net force acting? We have a 10 Newton force acting downward and a 4 Newton force acting against that 10 Newton force. So the net force is gonna be 10 minus 4 being equal to mass is 2 and acceleration a. So we'll just apply our math now. 6 upon 2 is 3. Answer is 3 meters per second squared. 14. All right, now let's move on to the next MCQ. Again, an inclined plane question. Okay guys, so in this question we have to consider all the different energy conversions. Okay, we know that the total energy or the total work which is done in this case has to be converted into gravitational potential energy, because there is a gain in height. So gravitational potential energy, there is a gain in gravitational potential energy plus kinetic energy, because if there is a change in velocity, then the change in kinetic energy will occur, and if there are some resistive forces existing or some frictional forces existing, then some work will also be done against them. In this case, they told us that a constant force F acts on the car and moves the car up the slope through a distance as at a constant velocity. Constant velocity would mean that the kinetic energy, change in kinetic energy is zero. All right, so no energy is being converted into kinetic energy. All right, so we can just assume that the kinetic energy is not being Uh, okay, so this tells us that since it's moving at constant velocity, none of the energy is being converted into kinetic energy. So the useful energy output does not involve kinetic energy. So kinetic energy is out. Now we are left with gravitational potential energy, and we are left with work done against friction. Work done against frictional forces, this is the energy that is wasted, right? And to calculate the efficiency, the formula for efficiency is the useful output energy divided by the total energy. This is efficiency. Okay, the total energy in this case is gonna be the constant force multiplied by the displacement. This is actually the work which is done by this constant force. So F multiplied by S, this is your total energy, total initial energy with total energy input. Now what is the useful energy output? Useful energy output is the gravitational potential energy. Now how to calculate the gravitational potential energy? Okay, basically to calculate the gravitational potential energy, first of all you need to identify the direction of the weight which acts downwards, mg, and identify this height. Okay, this height, we know that the horizontal height is s and this is alpha, so the vertical height is going to be s sine of alpha. So the work done against gravitational gravity, or work done against gravity, is going to be mg times S times sine of alpha. This is the useful energy output divided by the total energy input is F multiplied by S. Okay, the S and S can be cancelled down, and we are left with mg sine of alpha divided by F. Mg sine of alpha divided by F, and delta is the correct answer. Let's move on to the next MCQ. Number 16. A force of 1000 Newton is needed to lift the hook of a crane at a steady velocity. Again, steady velocity means none of the energy is converted into kinetic energy. Change in kinetic energy is zero. Moving forward, the crane is then used to lift a load of this mass at a constant velocity of this. Okay, at a velocity of this much. Okay, first it was moving at some constant velocity, then it started moving, then it moved a load of this much mass at this velocity. How much of the power developed by the motor of the crane is used in lifting the hook and the load? And assume that the acceleration of free fall is equal to 10 meters per second squared. All right. Okay, so how much power is developed by the motor of the crane in use to lifting the hook and the load? First, to lift the hook, it required 1000 Newton energy, force. Then the crane is used to lift a load of this much at this velocity. Again, the velocity is still constant, okay? No change in kinetic energy. Okay, there must be change in potential energy then, because it's being lifted. The work is done against friction. Sorry, against gravity. All right, so what's the power? Okay, so basically, this is the constant velocity, but this constant velocity, this is a hint for us. Let's assume that it's 0.5 meters per second. Let's assume the distance for 1 second. Okay, what's going to be the distance in 1 second is going to be 0.5 meters. So this crane actually moved the load along with the hook by a distance of 0.5 meter in 1 second. Can we calculate the power now? Okay, power is the work done per unit time. Work done is force multiplied by distance divided by the time for the power. Okay, what is the force? Force is actually the combined force of the hook and this load. Okay, the force of the load is gonna be the weight of the load is gonna be 1000 multiplied by 10 mg. Okay, and plus 1000, which is due to the hook itself. So it's gonna be 10,000 plus 1000, which is actually 11,000. So 11,000 is the force multiplied by the distance is 0.5. Okay, 0.5 is the distance divided by 1 is the time, and so the answer that we get is 5500 watts. Okay, 5500 watts is not the correct answer, but in SI units is going to be 5.5 kilowatts, and B is the correct answer in this case. Let's move on to the next MCQ now. 17. When ice melts, it contracts. Which row is correct for ice turning into water? All right, ice is contracting. What's happening to its density and what's happening to its the distance between the atoms? Okay, guys, just remember one thing. Water has anomalous behavior across 4 degrees Celsius. All right, 4 degrees Celsius is the temperature at which water has the maximum density, max density. Below 4 degrees Celsius, while it converts into ice, its density decreases. This is actually a fact and it's hidden in between its molecular arrangement. Okay, because volume of the, or basically the spacing between the molecules of water increases as we go from 4 degrees Celsius to 0 degrees Celsius. If the volume in that case increases, then the density will have to decrease. But now we are melting the ice. Okay, melting the ice would mean that we are going from 0 degrees Celsius to 4 degrees Celsius. This actually would mean that the density is increasing. Okay, if the density is increasing, what will happen to the distance between them? Okay, density increases. It could either be B or C or D, sorry, B or D. All right, what happens to the distance between them? Okay, distance depends upon the volume. All right, if the density is increasing, the volume of water or volume of ice is decreasing, right? If the volume is decreasing, then the molecules will come close to each other, and so it's going to be B. The distance between them decreases. All right, so it's going to be Bravo, right? B is going to be the correct answer. Now moving on to 18. All right, atmospheric pressure at sea level has a value of this much. The density of seawater is this much. At what depth in the sea would the total pressure be 110 kilopascals? All right, so assume that this is our sea level. All right, and they told us that at the height or at the sea level, atmospheric pressure is 100 kilopascals, and now at a certain height, sorry, the density of water is given. Now they're asking at what depth within the liquid will the total pressure be this much. Okay, to calculate the total pressure, we'll have to calculate the we'll have to add up the atmospheric pressure to the pressure within the liquid. Okay, the pressure within the liquid is the formula for pressure inside the liquid is rho gh, where h represents the depth within the liquid, g represents the gravitational constant, and rho represents the density, and pa is the atmospheric pressure, and pt is the total pressure. The total pressure that we are demanded is 110 kilopascals. So let's plug it in here. 110 kilopascals, which is equal to atmospheric pressure, which is 100 kilopascals, plus the density of water is 1020, and G is 9.81, and we need to calculate H. What is the H? All right, so let's apply our math. We get 0.999 meters as the height. All right, so this will round off to 1 meter. So answer option A should be the correct answer. Now let's move on to the next MCQ, number 19. All right, so 19, a spring is compressed by a force. The graph shows the compressing force plotted against the length L of the spring. Okay, so this is actually our compression force. So if the force increases, the length decreases to this value, and if the force decreases, the length increases, and if the original length is 100 millimeter. What is the spring constant of this spring? All right, to calculate the spring constant, just we need to do, okay, the formula for spring constant, F is equals to kx. This is the formula from Hooke's law. We know that force is proportional to extension or compression, right? So now we need to calculate the value of k. Okay, how to calculate the value of k? All right, so to calculate the value of k, let's take any one of the values. Okay, let's assume this point over here. Okay, the length at this point, when the force of 6 Newton is applied, the length is 70 millimeters. But guys, this is the length, this is the original length of the spring. This is the length or the total length of the spring due to this force. This is not the compression. This is not the value of x. The value of x is actually the difference between its original value and the new value. It's 30 millimeters. So 30 millimeters is the value of x. All right, you have now the value of x. You have the value of force. Can we calculate the k? All right, so the value of force is 6, which is equal to k times the value of x is going to be 30 millimeters. The milli must be converted into meters because we have to do the calculations in SI unit. The answer that we get is 200 newtons per meter, right? So delta is the correct answer. D is the correct answer. Moving on to the last MCQ of this lecture, 20. Okay, which graph represents the force extension relationship of a rubber band that is stretched almost to its breaking point? Okay, if you start increasing the force, extension will start increasing. Okay, extension will increase. After reaching a certain point, what would happen? Further increase in the force will result in a very small extension because now its elastic limit is over. Now it has reached near its breaking point. Okay, so this is actually the graph of a rubber band, a force extension graph for rubber band. But guys, rubber band is no longer a part of our syllabus, so you don't need to worry about this. It has been removed after the 2016 syllabus. Okay, in the 2016 it was removed, right? So it's not a part of our latest syllabus anymore.